So now let's try to have a sample problem for us to appreciate the theories we discussed. So let's have here a cable attached to the eye bolt in the figure, and it is connected from A to B with the force F with the magnitude of 500 Newton. So it is said in the problem that points A and B lie on the line of action of force F. So the vector F passes at point A to point B. So we need to represent vector AB, but vector AB is not vector F. We are just using vector AB to get the direction of vector F. Now we have to determine the rectangular representation of this force. So again, vector AB is not vector F. So in order for us to represent vector AB, let us first have the coordinates of points A and point B. So again, it is important for us to know which are the positive sides of the axis, because if we have wrong orientation of positive axis, we will have wrong interpretation of coordinates. So let's define point A in the figure. So this is X, Y, and Z. So A moves 4 meters away from the origin, and this is the positive orientation of x-axis. So that means we use positive 4. Now, point A does not have any movement relative to y-axis, so its y-coordinate is 0. And in terms of z-coordinates, that is positive 3. That's why we have point A having coordinate 4, 0, and 3. Now let's have the coordinate of B. Its x coordinate is 0. Y coordinate is 6 because it moves 6 meters from origin to the positive y axis. So we have 6, and it does not displace in z direction, therefore it is 0. Now, to get the vector representation of vector AB, that is simply 0 minus 4. Again, that is B minus A. So 6 minus 0 and 0 minus 3. Then we simplify that, we get the vector AB equals to negative 4i plus 6j minus 3k. Now, having vector AB, we can get the unit vector. So points A and B lie on the line of action of force F. We can represent vector AB in such a manner we can have the unit vector. Now, here's the thing. If you have the vector represented in 3D, or you already have the vector representation, you can easily get its corresponding unit vector by simply dividing it with its magnitude. So if you have a vector, you want to get its unit vector, simply divide the vector by its magnitude. Recall that this equation, vector F is equals to the magnitude of F times the unit vector. So if you want to solve for the unit vector of that vector, of this vector F, you simply divide the vector F by its magnitude, and we are doing that here. So we want to get the unit vector of vector AB. Why? Because the unit vector of AB is also the unit vector of F, because they have the same direction, and as we discussed, the unit vector gives direction. So to get the unit vector of AB, we simply rewrite vector AB and then divide it with the magnitude of AB. And the magnitude of AB is the sum of the square of its component. So we have negative 4 squared plus 6 squared plus negative 3 squared. And then the square root of that divided by each term here, you arrive with this unit vector. Now, we want to get, now the unit vector is here. I rewrite it in the upper portion of the presentation. Now we want to get the vector f. So to get vector f, multiply the unit vector with the magnitude of f, which is given 500 Newton. Now that is simply substitution. And then if you distribute 500 in each term here, you get the vector representation of force F. We have the magnitude of F, unit vector of F. Simplifying, we have negative 256 plus 384 minus 192 with I, J, and K. Now, as you can see, with the F being represented in 3 dimensions, you can easily see its component. So its negative 256I is the x component or the rectangular component along x-axis. That is negative because it is directed towards the negative orientation of x-axis. So if you have wrong orientation of x-axis, you might get the opposite answer. So in this case, negative 256 because your vector or the x component of vector f is towards the negative x-axis. Whereas this positive 384 is to the right, which means this is towards the positive y-axis, and 192 downward, negative 192 because it is towards the negative orientation of the z-axis. So there we have it, the vector f represented in 3 dimensions. Okay, so let's have another problem here referring to the figure. Let's determine the rectangular representation of position vector A and the 2 angles between A and each of the positive coordinate axes. So our objective now is to get A represented in 3-dimensional axis and the angle from the other 2 positive axes, since the angle measured from the positive z-axis is already given, which is 30 degrees. Now, let's try to solve for the components. So this time, let's try to solve components first to get the vector representation of A. So by trigonometry, we can simply get the value of AZ. So if you try to imagine a triangle with hypotenuse of vector A and the adjacent side of 30-degree angle is the AZ. And as you can see, AXY is also this one, AXY. We can determine it by trigonometry. Let's first have AZ. So from trigo, the z component AZ is A cosine 30. It is also similar to what we discussed, that the magnitude of vector times the direction cosine of the particular axis. So if this is the z direction cosine for z axis, you get the AZ component. So that is 12 times cosine 30 degrees. So your AZ now is 10.392. Now, we can determine AXY, or this is AXY, by using sine function. This is the hypotenuse and this is the opposite side of this theta z, which is equal to 30. Now AXY is equals to A sine 30 degrees, also equals to 12 sine 30. And then we can have AXY equal to 6 meters. So that is AXY, 6 meters. And if we have already the value of AXY in this case, we can get AX and AY. Now, if we already have AX and AY and AZ, we can simply represent vector A. Now this problem is intendedly shown here because this is one way of solving or representing vectors using components. So the previous problem, we used the unit vector to represent a particular vector. This time we use the components to represent the vector. Now let's resolve axy to ax and ay. So if we have the value of axy as 6 meters, so we can solve by trigonometry the value of ax, and that is 6 cosine 40, that is 4.596 meter. And also ay, we use sine function in this case. So sine axy times sine 40, we have ay, and that is 6 sine 40, we get 3.857 meters. So summing up the results, we have ax equal to 4.596, ay equals to 3.857, and az equal to 10.392 meter. So these are the three components, and the vector representation of A is in this form. A is equals to AXI plus AYJ and AZK. We simply substitute the values of the components we have determined from trigonometry, and that is A is equals to 4.60 in this one, plus 3.86J plus 3.92K. Now we can have the angle. So we answered question 1 already. We have represented vector A. Now we need to get the angle between A and each of the positive coordinate axes. So let's try to solve. Recall that the angle measured from the x-axis is the x component, magnitude of the x component of vector, and the magnitude of vector A in this case. So we use cosine theta x equals ax over A. So for theta x, the magnitude of A is already given, equal to 12. So let's get the value of theta x, 4.596 over 12, and use our cosine. We determine the angle measured from the x-axis equal to 67.5 degrees. Now let's try theta y. So this is the definition of direction cosine. Again, cosine theta y is equals to ay over a. So substituting the values, we have our cosine -1. Our cosine equals to our cosine of 3.857 divided by 12. We have now angle measured from the positive y-axis, that is 71.3 degrees. Now let's try to prove this should be correct, that cosine theta z, although it's already given that it's 30, let's try it still. So cosine theta z is equals to az over a. Now we have az is equals to 10.392 and a equals to 12. Solving for theta z, we have 30 degrees. Okay. Let's have another problem. So the pulley shown in figure is subjected to the belt forces P and Q. Using rectangular components, determine the magnitude and direction of the resultant. So this is simply a two-dimensional vector analysis. So recall that P has two components, Pxi plus Pyj. So this is vector along x-axis and vector along y-axis. Adding them up yields to the vector P with a magnitude 120 Newton. So to get the x component of P, this is because this is 30 degrees, that is simply 120 cosine 30 degrees plus the y component, or the magnitude of the y component of P is 120 times sine 30j. So we have now the value of P equal to this one. Now let's try to solve the rectangular representation of Q. We have Q is equals to Qxi plus Qyj. So the same case, we will do the same thing here. So let's have the x component Qx and the y component Qy. Now Qx is equal to 100 cosine 70 degrees because of using cosine function. So make sure that this is negative because a negative sign means that the x component, sorry, this is Qx and this is Qy. So Qx is directed to the opposite side of the positive x-axis, therefore this is negative, and likewise Qy is directed opposite to the positive y-axis, therefore it is negative 100 sine 70. Now we have the vector representation of P and Q, and the resultant of P and Q is R. So to get R, we simply add P and Q. So as we discussed, when we add components or we add vectors, their components should be added. Okay? So if you try to see here, you add the values of I of P. So 120 cosine 30 is this one, and minus 100 cosine 70 is this one. And for the J, simply add the coefficients of J. We have 120 sine 30. I have just directly computed the value of this one. And minus 100 sine 70, this one. So we get the sum of P and Q by adding up the coefficients of I and coefficients of J. Now we get the value of the resultant. R is equals to 69.7I minus 34J. Now the magnitude of the resultant is simply determined by summing up its component. So we have R squared is equals to 69.7 squared plus negative 34 squared. We have the value of the resultant acting on the pulley equal to 77.6 Newton. Okay. So for the direction, so if the component is positive 69.7 and the negative 34, that means downward, we can define by theta. So in this problem, theta is preferred to be measured from the x-axis in a clockwise direction. So we have here theta is equals to arctan 34 over 69.7. Then you have angle 26 degrees. But if it's measured from the positive axis in a clockwise manner, you can say that it is negative 26 degrees. Okay, another problem. Now we have the resultant. Let's try to compute for the components. So if R is the resultant of the forces P and Q, find the magnitude of P and Q. Okay? So the resultant representation or the rectangular representation of resultant vector R is its x component and its y component. So the x component of R is simply 360 cosine 25 using cosine function, and the y component is simply 360 sine 25. Now, simplifying the terms, we have vector R represented here equal to 326.27I minus 152.14J. Okay, let's write vector R here at the bottom. Now, let's take a look at vector P. Now, vector P has two components because this is 2D. So the x component of vector p is p cosine 30 and its y component is p sine 30 from the figure py and px. So simplifying this one, we have vector p is equals to 0.8660 p, or the magnitude of p, plus 0.50 p j. Okay, that's it for vector p. Now let's try vector q. So vector q again, or similarly, has x component, which is equal to negative q sine 30 because of this one, using trigo. And if this is, again, if this is your q, and if you're looking for qx, you use negative q sine 30. And if you're looking for qy, you use cosine. So negative q cosine 30j. Now simplifying that, we have 0.50 q minus 0.8660 q. Now let's list down all of the vectors we had. As you can see, there are two unknowns, p and q. Therefore, we need two equations that relates p and q. So let's see what are the relationships where we can have p and q. So recall that the x component of r is the sum of the x components of p and q. So the x component of p plus the x component of q should yield the x component of the resultant. So this is our first equation wherein we can have p and q. So we still need another equation for us to solve p and q. Okay, so that's it. Also, if you add up the y components of p and q, you must have the y component of the resultant, or r. So that is 0.50, that is 0.50p plus minus 0.8660q equal to, I'm sorry, this is 152. So just check it out. This might be a little error, but still the concept is okay. So solving the two simultaneously, is it 125 or 152? Let me just check. 152 it is. So this is 152. So solving the two equations simultaneously, so if you want to solve for p in terms of q, then you will substitute the value of p you determined from a in terms of q. Then you are left with only q values in this second equation. So, or otherwise, if you want to solve for q in terms of p, then substitute the value of q to get value of p. Or you may use your calculators to solve for the two unknowns. So solving them simultaneously, we have the value of p equal to 717.26 and the value of q equal to 589.79 kilonewton. Okay, so if you want to learn more, or if you want to practice, I want you to have these problems answered so you can have or so you can really appreciate the subject more. So answer these practice problems. So the theories here, and also the practice problem for computation. So just pause your screen if you want to copy all these problems, and the figures is shown here. So please have a copy. And that's it. I want to thank you all for watching the video. I hope I help you in understanding more about vectors. So for the next topic, we will have the operations of vectors like dot product and cross product. Again, thank you.